Hi, welcome to the video lecture on software processes part 1. The agenda is like this. We have nature of software, changing nature of the software, and the generic process framework or the GPF of the software to be discussed in this video lecture. So we might note that computer software continues to be the single most important technology on the world. So 60 years ago, no one would have imagined or even predicted that software would become such an indispensable technology for all kinds of applications. So basically, we are correcting, adapting, and enhancing the software, and this is called the maintenance activity. And maintenance activity basically absorbs more people and resources than any other work applied in the creation of the software. So there are some typical questions that were asked when modern computer systems were built, like why does it take so long to get the software finished? Why are development costs very high? Why cannot we find all errors before we deliver the software to the customer? Why do we spend so much time and effort maintaining the existing programs? And why do you continue to have difficulty in measuring progress as software is developed and maintained? So you can probably find out answers by yourselves for these questions, and you can always take it as a debate as well. So if you look at software is a product, which means it transforms information from one form into another. It basically delivers computing potential of the hardware and networks. Also, a software is a vehicle for delivering a product. So when I say vehicle, it basically controls other programs. For instance, the operating system is a program that basically controls your computer. It affects communication. For example, a networking software that is installed on a router basically affects communication. It helps to build other software where you can use it as a simple tool or an IDE, the integrated development environment, to build other software using your software as the base. Now coming to the nature of the software. So what is a software? Software can be defined as follows. It is a set of instructions where you execute them to provide the desired features, function, and performance. It can be called a data structure, which is basically used for manipulation of operations, or it could be called as a document. The operation and use of a program is probably written in that. So whenever you go for developing a software could be developed for a particular customer, or you can probably develop a software to be marketed in the general market. So basically, it could be divided into two categories. One is called generic, which means it is developed to be sold to a wide range of customers. For example, the MS Office. The next category is called bespoke, otherwise called the custom, which is basically developing software for a single customer according to his specification. If you look into some kind of distinctions between the hardware and the software, a hardware is manufactured whereas a software is developed or engineered, rarely manufactured. A hardware wears out over time. A software does not wear out, instead it deteriorates over time. A hardware is basically built using components where you just assemble the components together to get a hardware component. The software is always custom built. A hardware is relatively simple but a software is quite complex. So when you talk of manufacturing versus development, once a hardware product is manufactured, it is almost near to impossible to modify it. But if you look into the software, a software is going to be routinely modified and upgraded. In hardware, hiring more people will allow you to accomplish more work, but the same does not hold true in software engineering. I have talked about this in the video lecture titled Introduction to Software Engineering. Unlike hardware, software costs are concentrated in design rather than production. This basically shows how a hardware is different from a software. This diagram is called the failure curve for a hardware. This picture is most famously called the bathtub curve, as this basically resembles a bathtub. You have time on the x-axis and failure rate on the y-axis. So as time progresses, initially you have something called an infant mortality. Then as time progresses further, it is a flat curve. Then over time, the hardware basically wears out, because of age. So this is typically called a bathtub curve or the failure curve for the hardware. If you look at the failure curve for a software, so basically there are two curves. The lower one is called the idealized curve, which means it will happen only in ideal conditions, which is almost not possible. The actual curve is on the top. On the actual curve, you will probably see certain spikes. These spikes are basically increased failure rates due to what we call it as a side effect. What is a side effect? So whenever software changes over time, it propagates what is called a side effect to the nearby modules, and those are the spikes that you could see on the diagram. Whenever a hardware component wears out, it is replaced by a spare part, but there are no spare parts for a software. So therefore, software maintenance involves considerably more complexity than a hardware. So when you talk of component-based versus custom-built, hardware products typically employ many standardized design components. It is just, assemble them together. Most of the software still continues to be custom-built. The software industry also seemed to slowly move to what is called a component-based construction, where I probably buy certain software components off the shelf and then probably try to assemble them together, tweak a bit, and then probably deliver it to the customer. And this definitely helps to save time than writing a software from scratch. So if you look at the software characteristics, software is developed or engineered, rarely manufactured. It does not wear out but only deteriorates over time, and software continues to be custom built as industry is slowly moving towards component-based construction. If you look into the changing nature of software, there are softwares that come in different varieties and flavors, like the system software, application, engineering or scientific, embedded, product line, web or mobile apps, and AI. Initially, there were only two major categories of software called the system software and the application software. System software is a collection of programs that are written to service other programs like the OS, the compilers, and so on. And these programs have a heavy interaction with the hardware and so on. The application software are standalone programs that are basically written to solve very specific users or business needs. And now we have a lot of other varieties that have come up. One is called the engineering or scientific software, which basically uses what I call it to be the number crunching algorithms. So for example, the CAD, the computer aided design, or any kind of software that uses what is called the system simulation in areas like molecular biology to automated manufacturing and so on are called the engineering or scientific software. Then we have the embedded software, which is very famous. It resides in a ROM called the read-only memory and basically used to control products and systems like the keyboard control for a microwave oven or a keyboard control for a fully automatic washing machine and so on. Then we have the product line software, basically designed to provide a very specific capability by many different customers. And one simple example of this product line software is the word processing software or the spreadsheets or the computer graphics and so on. Then we have the most common web or mobile apps which everybody is more familiar with, and they contain little more than a set of linked hypertext files, and they not only provide standalone features or functions, but they are also integrated into corporate databases and business applications, and that is the power of the web or the mobile apps. Then we have the AI, the artificial intelligence software, which uses what we call it as the non-numerical algorithms to solve complex problems that are not amenable to computation or straightforward analysis. Expert systems, game playing, and robotics are certain examples of the AI software. The changing nature of software is divided into four broad categories, namely the web apps, the mobile apps, cloud computing, another buzzword nowadays, and product line software. Whenever you talk of the web apps, otherwise called the web applications, the web apps have evolved into sophisticated computing tools that not only provide standalone functions to the user, but they are also integrated into corporate databases. So they provide full computing potential in many applications. So sophisticated relational database structures will lead to entirely new web apps and so on. Then we have the mobile apps, and this has evolved to connote software that has been specifically designed to reside on a mobile platform. So this will definitely have a UI that takes advantage of the unique interaction mechanisms provided by the mobile platform. The mobile app has direct access to the hardware characteristics like the accelerometer or the GPS, and then they will provide the local processing and storage capabilities, and that is how you are able to use a lot of applications on your mobile, like the Google Maps that basically uses the GPS and so on. Then cloud computing is another buzzword in the 20th century. So cloud computing encompasses an infrastructure or an ecosystem that will enable any user anywhere to use a computing device and it uses what is called shared computing resources. So we have two things, the front end and the back end services. The front end will include the user, otherwise called the client device, and the application software, which is obviously a browser. And through this, I'm going to probably access the backend. The backend basically will comprise of what is called the server and related computing resources, databases, server resident applications, and so on. And all these are coordinated and monitored by a set of protocols for access to the cloud and its corresponding resources. So this is the diagrammatic representation of cloud computing, where you have the application, the platform, the infrastructure, and the devices outside of the cloud. Then you have the product line software, which is a set of product software intensive systems that will share a common set of features that satisfy specific needs of a particular market segment. So they are all developed using the same underlying application, the same architecture, and they are all implemented using a set of reusable components, that you can probably reuse it across the product line, and that is what is called the product line software. So to come back quickly to the definition of software engineering, so which says application of a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software, or the application of engineering to software. So software engineering layers. So why layers? Different layers. The obvious reason is it is easy to manage. So software engineering is a layered technology. So if you look at the layers, the lowermost layer is the quality, on which lies the processes, on which lies the methods, and on which rest the tools. So the bottommost layer you can obviously note is called the quality. Any engineering approach must rest on an organizational commitment to quality. And we would say that the bedrock of software engineering is the quality focus. The foundation for the software engineering is the process layer that exactly lies above the quality focus. So a process is a framework established for effective delivery of technology. So the process will form the basis for management control of projects and establishes the context in which technical methods are applied, work products are produced, milestones are established, quality is ensured, and change is properly managed. Yeah, that is what is called a software process. Then methods lie above the process. The method basically talks of the technical how-tos, how to do things. So it will probably comprise of communication, requirements analysis, design, modeling, program construction, testing, and support. So software engineering methods rely on a set of basic principles that govern each area of technology. So tools rest on the methods. The tools provide automated or semi-automated support for the processes and the methods. So when tools are all integrated together, and then we call it the computer aided software engineering. Coming to the software process. The software process is a collection of activities, actions, and tasks that are performed when some work product is to be created. So, what are the differences between an activity, action, and a task? An activity basically talks of a broad objective. For example, communication with stakeholders is an activity. This activity will be applied irrespective of the domain, the size, the complexity, or the rigor of the project. The next one is called the action. For instance, architectural design is an action. An action consists of a set of tasks that basically produce a major work product like a model. What is a task? A task is a small, well-defined objective. For example, conducting a unit test is a task. So, once the task is performed, I will get what is called a tangible outcome. So, a process is definitely not a rigid prescription of how to build a software. So, a process is an adaptable approach that enables people doing the work to pick and choose the set of actions and tasks. So, my objective or goal is to deliver software in a timely manner with sufficient quality so that all stakeholders are fully satisfied. So, in order to do this job, we have something called the process framework. The process framework establishes the foundation for a complete software engineering process by identifying small number of framework activities, and this can be applied irrespective of the size, the complexity of the project. In addition, it also consists of a set of umbrella activities that can be applied to the entire software process. So, a GPF or a generic process framework consists of 5 activities. It starts with communication. Communication is very important. It is critically important to collaborate with the customer. Before you begin any kind of a technical work, communication needs to start. The next one is called planning, which basically defines a set of technical tasks to be conducted, risks involved, resources to be utilized, work products that will be produced, and so on. And more importantly, the work schedule will be prepared during the planning activity. Next comes the modeling. Modeling is creating a sketch, so that you will be able to understand the big picture. Then comes construction. Construction is what you design the previous activity should be built, and this will obviously combine code generation that could be done either manually or automated, and testing definitely needed to uncover errors in the code. You can fully automate tests, or you can semi-automate, or you can do manual testing as well. And the last one is called deployment. Deployment basically gets you a complete software that is delivered to the customer, who will evaluate the product and provide sufficient feedback based on the evaluation. So whenever you talk of an umbrella activity, in general, an umbrella activity is applied throughout a software project, and this will help the software team to manage and control progress, quality, change, and risk. Typical umbrella activities include risk management, technical risk reviews, SQA, SCM, reusability management, software project tracking and control, and so on. So we have something called the process adaptation. Previously, we said that the software engineering process is not a rigid prescription. Rather, it should be agile and adaptable. Therefore, a process adopted for one project might be significantly different than a process that is adopted for another project. So what could be some kind of differences you would obviously find in the process adaptation? For example, the overall flow of activities, actions and tasks, the interdependencies, the degree to which the work products are identified, then the overall degree of detail and rigor, level of autonomy, the degree to which team organization and roles are prescribed, and so on, could sometimes be some typical differences among the different software products. So, to give you a quick summary of this lecture, software is the key element in the evolution of computer-based systems. The nature of software is definitely changing between web, the mobile, and the cloud. The software engineering encompasses processes, methods, and tools, and obviously the bedrock is quality. Then the software process incorporates 5 framework activities, namely communication, planning, modeling, construction, and deployment, and this is applicable to all software projects irrespective of the size or the complexity. And lastly, software engineering practice is a problem solving activity that will definitely follow a set of core principles. So thank you, and my next video will basically focus on the software process part 2. So stay tuned till then. Thank you.